Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to set up integrals for area bound between curves represented in polar coordinates. So what we're looking at here, we're looking at two curves, r equals 4 sine theta and r equals 3 cosecant theta. We're going to try to set up integrals to find the area bound inside of this curve and below this curve. And I'll talk about why the language below that curve here in just a moment. So first I'm going to talk about graphing these things. All right? All of these problems start with a good graph. You know, in the old saying that a picture is worth 1,000 words, in math and physics it's 2,000. So let's talk about the curve r equals 4 sine theta first and how to graph it. Now, a good place to start when graphing these is just a good Cartesian graph of r against theta. I can do a little better than that. Okay, r against theta. This is a standard sine wave. It's going to get as high as 4, as low as minus 4. It's very important to know what kind of the important angles are within that graph. So this guy right here would be pi over 2. That's where the sine function is a maximum. Pi, 3 pi over 2, 2 pi. All right, so now we use the Cartesian graph to sketch our polar graph. So the first thing to notice is if theta is 0, r is 0. So in our polar graph here, we're going through 0, 0. I'm going to put another point on there before I talk about in between them. When theta is pi over 2, r is 4. So in this graph, theta of pi over 2 is this angle. 4 units up is right there. I'll go ahead and get rid of that stuff. So that's the point in polar, 4 pi over 2. Now let's talk about how these connect. When theta is between 0 and pi over 2, you notice that the radius is getting larger as theta gets larger. So what's important to realize is in our graph, okay, and imagine this little dot here being my point. So as theta gets larger, the dot is getting further from the origin. And that's mapping out a circle. Okay. So that's looking something like this, again, for this part of the curve. Right. Then when we go from pi over 2 to pi, the radius goes to 0. Right? The radius starts at 4 and goes to 0. So pi over 2, we're here. As we sweep, as the angle changes to pi, radius goes to 0. Boom. Kind of a twisted circle, but that's a circle. If it doesn't look like a perfect circle, maybe the viewer should check their resolution on their screen. All right, so now let's talk about the second curve here, r equals 3 cosecant theta. This one can be graphed pretty easily by recognizing that cosecant theta is 1 over sine. So another way to write this same curve is sine theta times r equals 3. And standard terminology, or the standard method for going back and forth between polar and Cartesian, x is equal to r cosine theta and y is equal to r sine theta. So this is a graph of y equals 3. Now, y equals 3, if I put it on our picture here, is a horizontal line up at 3. So there's a graph of our second function here. So what we're looking for now is the area inside of our circle and below the line. So if I did kind of a quick little dirty shade here, that'd be all this stuff. Okay. Now, the next step is to draw an area element in polar. I don't need this anymore. Let me make myself some more room. Now, our area elements in polar are little triangles. I'm going to try to draw kind of a pretty good one here. So I'm going to draw a triangle somewhere in this region. I like to use red for my differential elements. All right, so we have to imagine a triangle that looks something like this. When I draw my differential triangles in polar, I try to make it so that the curve touches the center of this leg of the triangle. Now, a very important thing to recognize, the distance here, the length of this triangle, is defined by the circular curve, the r equals 4 sine theta. However, when we break through this angle, which we'll calculate here in a minute, the radius is now defined by our linear curve. So I'm going to draw a second differential element. So for this problem, it's very important to realize that the curve defining the radius of our triangle depends on where we're at. Therefore, it's going to take two integrals to work this. I'm going to also apply another standard little trick. Looking at the symmetry of the problem, I'm just going to integrate this 0 to pi over 2 and then multiply by 2. Now, when I say integrate to 0 to pi over 2, there is some angle that we're going to need. The radius changes how it's defined at this point. We're going to have to find that angle first. At this point, the two radii are the same, so we can say that 4 sine theta is equal to 3 cosecant theta. Now, cosecant is 1 over sine, and if we move that sine over here, this is now going to read sine squared theta equals, and I'm going to go ahead and put the 4 over on the right, 3/4. So sine theta is equal to plus or minus root 3 over 2. Now, both the cosecant function and the sine function are positive in the first quadrant here. So we're looking for where sine theta is equal to root 3 over 2. When we take the inverse sine of that, I think we get pi over 3 out of that. Sine of pi over 6 is 1/2. Yeah, sine of pi over 3 is root 3 over 2. All right, so what we're going to do now is we are going to integrate 0 to pi over 3 using this curve, and then pi over 3 to pi over 2 using the second curve for our radius. Make a little room before I do that. All right, so our total area is going to equal 2 times. And again, 2 times because I'm only doing the first half of this using symmetry, and then we'll just multiply by 2 to get the second half. First integral is going to be 0 to pi over 3, r squared d theta, where r is defined by the circle 4 sine theta. So 4 sine theta squared d theta. This will map out the area bound in this region. Oops, over 2. Area of a polar element, 1/2 r squared d theta. Right. Now we want to get the second area. That's this triangular looking piece actually. And again, we could probably do it geometrically, but I'm going to go ahead and set it up as an integral in polar coordinates. So that's going to be the integral. Now we're starting at pi over 3 and going to pi over 2. 1/2 r squared d theta. Now the r, pardon me, is defined by the curve 3 cosecant squared. I'm sorry, 3 cosecant theta. And there's our setup. This expression should give the total area bound within the circle and below the line. Now, the purpose of this video was how to set up the integral. I'm not going to work through that integral in this example. I will just talk a little bit about how to do them. So this guy right here, this is 16 over 2, which is 8 sine squared d theta. This would simplify down using sine squared theta equals 1 minus cosine 2 theta over 2. So this itself will break into two integrals. Integral cosecant squared let's see, I don't remember. Maybe one of the trig functions has a derivative of cosecant squared. Probably what you can do with this is apply Pythagorean theorem, sine squared plus cosine squared equals 1. And let me write this down. You can get other forms, including I want a form with cosecant squared by dividing by the appropriate term. If I divide this by sine squared, it would become 1 plus cotan squared equals cosecant squared. So I think what I would do is probably rewrite this as 1 plus cotangent squared, break it into two integrals. And then cotangent is cosine over sine. You can do 1 plus cotangent squared. I guess the u sub on that's not going to work. I'll just say this. This integral can be done numerically in Excel, no problem. So again, the point of this problem wasn't how to work out all these little integrals. The point was how to set up the integrals for area calculations, and I think that that's good enough. I'm just going to stop that right here. Have a great day.